For this example, we are going to graph this function and then also describe the domain range, any asymptotes that are there, the end behavior using limits, and also where the function is increasing or decreasing. When I take a look at this equation, I see we have y equals log base 3 of x. This is one of our parent functions. There's no addition or subtraction or any other numbers in there. We just have our log with our base and our value of x. For all parent functions, our graph will go through the point 1, 0. We have an x-intercept at 1. Our graph will also go through the point base comma 1. So this particular problem is going to go through the point 3, 1 because the base of our log is 3, and also has a vertical asymptote right on the y-axis, which has the equation x is equal to 0. So making a quick sketch of the graph using these features. We have an x-intercept at 1. Our graph also goes through the point base comma 1, which for this particular problem happens to be 3 comma 1. And we do have a vertical asymptote right on our y-axis, and the equation for that is x is equal to 0. The shape that we have for logarithmic parent functions, our graph will start just to the right of our vertical asymptote down at the bottom. It will go up through this first point, curve, and continue going up and to the right like that. So there's a reasonable sketch for function f. From there, we are supposed to go through and come up with our domain and our range and the equation for any asymptote that we may have. Let me do those three first. For our asymptote, we know where that's at. That is at x is equal to 0. And because our asymptote is a vertical asymptote and has an x here, we can use that actually to help with the domain. Copying the x and the 0 down into the domain in between, I'm going to need a symbol there. And if you take a look at this graph, we have a vertical asymptote here on the y-axis. And our graph is completely over to the right, which are all of the bigger values of x. We don't have anything that has smaller values of x. All of our points are over to the right. So the domain is x is greater than 0. The range, those are our y values, and this graph goes all the way down to -infinity, and as this goes up and to the right, it does get less steep, but it's going to continue going to the right and up and right and up and right and up. So it's going to go up for forever. So the range is all real numbers. We are also supposed to determine the end behavior, and we're going to do that using limits. Let me do the right end first. That one's a little bit easier for these graphs. If you take a look at the right end, if you go over to the right as far as you can, this graph goes all the way out to +infinity. It keeps going over to the right. So using limit notation for our right end behavior, we would have the limit as x approaches infinity. We can go over to the right for forever. And what we need to do is we need to describe is what is the height of the graph? What is our y value, or what is f of x doing over on that right side? So as this graph goes upward, as this graph goes to the right for forever, it continues going upward. So it's going to the right and up, and to the right and up, and to the right and up. So it is going very slowly upward to +infinity. It's going to the right much more quickly, but this graph will go forever upwards. For our left end behavior, we want to see how far over to the left our graph goes. And this graph does not go over to the left to negative infinity. There's a vertical asymptote here, which kind of blocks the graph. The graph has an x-coordinate here of 3. Here's an x-coordinate of 2. Here's an x-coordinate of 1. There's a point here that would have an x-coordinate of about half. As you continue going to the left, we get really close to an x-coordinate of 0. So for our left end behavior, we would have the limit as x approaches, and when you go over to the left as far as you can go, you don't go over to negative infinity. You can't go past the asymptote. So what we're doing is we're getting really close to an x-coordinate of 0. When you go over to the left as far as you can, we're getting very close to an x-coordinate of 0. You can approach 0. You can approach this vertical line from either the left side or the right side. And we should use some notation here to describe what's happening on that graph. We are approaching 0 from the right side. So how we do that is up here where normally we would put an exponent. Math people would put a little plus or a little minus. It would be better maybe if we put in R for the right side and an L for the left side, but math people use a little plus or minus instead. Plus means the right side. Those are the bigger numbers. If it was coming at it from the other side, from the left side, we would be using smaller numbers, L, which would be a subtraction symbol. So as we go over to the left, we are approaching our vertical asymptote from the right side, from the numbers that are a little bit bigger. So I'm going to put a little plus there. And then we need to describe what our height is doing as that happens. So as you get really close to an x-coordinate of 0 from the right side, our graph goes down to a height of negative infinity. The last thing that we need to do is we need to describe where this graph is increasing and where this graph is decreasing. Logarithmic function graphs are either increasing or decreasing the whole time. So the answer to one of these is going to be none. And the answer to the other one is everywhere, which is described by the domain. So the answer to one of these is going to be the domain, and the other one is going to be none. So as you travel along your line from left to right, this graph is going upward the whole time. It is increasing the whole time. So it's increasing the whole time, so we copy the domain down there, and this graph is never ever decreasing. So we fill that in with none.